In this video, we'll discuss problems and conceptual exercises of chapter 3 from the book James Walker. Now in this question we are given that a passenger on a stopped bus noticed that the rain is falling vertically just outside the window. So he noticed that the rain is coming like this, just vertical, falling vertical. So this is the velocity of the rain relative to ground, because at this moment the bus is standing, not running. So this should be the velocity of the rain relative to ground. Now when bus moves with a constant velocity, the passenger observed that the falling raindrops are now making an angle of 15 degrees with respect to vertical. So what it says, that when the bus started moving, so this should be the velocity of the bus relative to ground. When the bus started moving, he noticed that the raindrops are making an angle of 15 degrees with the vertical. That means the raindrop now are coming like this. This will be the velocity of the rain relative to bus. This is very important. And this angle is theta, which we are given to be 15 degrees. Now there are two parts in this question that we need to solve. In the A part, we need to find the ratio of the speed of the raindrop to the speed of the bus. Now, by using the concepts of relative motion, we can write that the velocity of the rain relative to ground, this will be equals to the sum of velocity of rain relative to bus plus the velocity of the bus relative to ground. This thing we can write. And we can also make a vector diagram for this. So VRB, we have this thing. So this is VRB. And VBG, we have this thing. This is VBG. And VRG will be shown by this vector. So this is VRG. So it's basically a right angle triangle. And what we need to find in the A part? The ratio of speed of a raindrop divide by the speed of bus. This is what we have to find. Now this angle is 15 degrees. So we can use this right angle triangle to solve this problem, A part. From this right angle triangle, we can say that VRG is VRB cosine theta and VBG is VRB sine theta. So this we can write, this is VRB sine theta. This thing we can write. And from here, this VRB and VRB will cancel and we'll get this is equals to 1 over tangent theta. And theta we are given with 15 degrees. So we can put it here. So VRG over VBG, this will be equals to 1 over tangent theta is 15 degrees. So that will be equals to 3.7. So this will be the answer for the A part. Now next, in the B part, we need to find the speed of the rain drop given that the bus is moving at a speed of 18 meters per second. So we'll be using this equation, this one. From here, VRG will be equals to 3.7 times VBG, and VBG we are given as 18 meters per second. So this should be equals to 3.7 times 18 meters per second, which comes out to be as 67 meters per second. So this is the answer for the B part. Now in this question, we are given that vector A points in the negative x direction. So we know the direction for vector A, but we don't know its magnitude. So I'll be first drawing the vector. So this is our vector, this is A vector, which is along the negative x. Now the vector B points at an angle 30 degrees above the positive x axis. Now here also we just know the direction, we don't know the magnitude. So we can make the vector B. So this is our vector B and this angle is 30 degrees. And since we don't know the magnitudes, so we can make it to be dotted, something like that. So this is our vector A and vector B. Now next we are given that vector C has a magnitude of 15 meter and points in a direction 40 degree below the positive x. So vector C, we have this is our vector C, which is below the x-axis, and this angle is 45 degrees. Sorry, 40 degrees, not 45. This is 40 degrees. Now we are also given that the sum of vector A plus B plus C is equals to 0. And then we need to find the magnitudes of the vector A and vector B. So this is our question. Now because it is given that vector A plus vector B plus vector C is equals to 0, then we can say that the x and y components of the vector independently should be equals to 0. What I want to say is that the x component of vector A plus the x component of vector B plus the x component of vector C should be equals to 0. Similarly, AY plus BY plus CY, that should also be equals to 0. Now we'll be using these two equations to solve this problem. Now from this equation, this vector is along the negative x, so there should not be any y component. So this thing we can write, this thing should be 0 plus. Now by, this will be equals to minus cy. This thing we can write. Now cy is the y component of vector C, and this is our vector C. So this will be its y component, and it's along the negative x, negative y. So cy, this would be C sine 40 with a negative sign because it's along the negative y. That would be equals to minus. Now magnitude for C is 15, so 15 sine 40. So we can put it here. So by, this will be equals to negative of negative 15 sine 40, which is equals to 9.64 meter. So we have obtained the y component for vector B. Let me show it on the figure. So this is our x component, this is bx, and this is our y component by. So we have calculated by. Now from this right angle triangle we can easily calculate bx, and we can write that tangent 30 degree, this will be equals to by over bx, right? And from here we can write bx is equals to by over tangent 30 degree. Now by we have 9.64, and this is tangent 30 degree. We can solve it and we'll get this value to be 16.7 meter. Now we have calculated bx and we have calculated by. Now we can easily calculate the magnitude for b. So b will be equals to under root bx whole square plus by square, so that would be under root bx. We have 16.7 and it's squared, plus by we have 9.64 and it's squared. Now on solving this we'll get this value to be 19 meter. So this will be the magnitude for B vector. Now next we have to calculate the magnitude for the A vector. So for that I can use this equation, this one. Now AX plus BX plus CX is equals to 0. Now bx we know. Now cx, what is cx? So let me first represent it on the figure. So this will be cx, and from here we can write that cx will be c cosine, and this is 40 degree. So c cosine 40. Now c is 15, so 15 cosine 40, so that would be equals to 11.5 meter. Now we can put it here, AX as it is, BX we have 16.7 meter plus CX is 11.5 meter is equals to 0. Now from here AX comes out to be as minus 28 meter. Now the vector A have no y component. It have no y component. So this itself will be the magnitude for vector A. But this negative sign will be removed because in magnitude we don't consider the sign. So this is 28 meter. So this will be the answer for the magnitude for the A vector. Now we'll discuss couple of problems which are based on this passage, as you can see on your screen. So first I'll make you understand what is all given in this passage, and then we'll discuss those problems. So we are given with this figure, and here you can see this prey is moving along the positive y with a constant speed of 0.750 meter per second. So I can write it here, this Vp we are given to be 0.750 meter per second. Now next it says that the dragonfly moves at an angle of 48.5 degrees to the x-axis. So this angle and this is the butterfly, here you can see this angle is 48.5 degrees. Now it's moving with a constant speed, so this is V0 we are given. Now if the dragonfly chooses its speed correctly, the line of sight from the prey to the dragonfly will be in the same direction parallel to the x-axis in this case. So what they are saying is that if the dragonfly chooses the speed correctly, then this is the line of sight, this will remain parallel to the x-axis. This is what they are saying. Now let's discuss the first question based on this passage. So this is the first question. It says that what speed must the dragonfly have if the line of sight, which is parallel to the x-axis initially, is remain parallel to the x-axis. So what it says that this what should be the value of V0 such that the line of sight remains parallel to the x-axis throughout the motion. So what we can conclude from this question is that the y component of V0 should be equals to the y component of this Vp, and the prey is itself moving along the y-axis, so this should be the y component for prey. So Vp y, this is equals to 0.750 meter per second. And what would be the y component for V0? This will be V0 sine theta. This is the y component for the dragonfly. Now we can equate these two. So we can write that V0 sine theta is equals to 0.750 meter per second, and theta we have 48.5, so I can put it here, this is 48.5. Now we can solve it for V0, and this value comes out to be as 1.00 meter per second. So this is the answer for this question. Now this is the second question based on this passage, and it says that if the dragonfly approaches its prey with a speed of 0.95 meter per second, then what angle theta is required to maintain the constant line of sight? So Vd in this case, this is given to be 0.950 meter per second, and then we are asked this angle theta, what should be this angle theta so that the line of sight is parallel to the x-axis. So here also the y component of Vd should be equals to the y component of Vp, this is meter per second, right? So we can write that Vd sine theta, this should be equals to Vp, and Vd we are given to be 0.950 meter per second sine theta, this will be equals to 0.750, and from here this is in meter per second, and from here we can write that sine theta, this will be equals to 0.750 divided by 0.950. From here we can easily find theta, and theta comes out to be as 52.1 degrees. So this theta should be 52.1 degree. Now in this question we have to refer the example 3-11 to solve this problem, and we have discussed this example in our previous videos, so do click on the bell icon to see that example. Now in this question what we are given is the speed of boat relative to water is 7.0 meter per second. So this is the speed of boat relative to water, this is 7.0 meter per second. Now next it says at what angle to the x-axis must the boat be headed if it is to land directly across the river from the starting position. So it says what this angle theta so that the speed of the boat relative to ground is perpendicular to the speed of water relative to ground. This is what it says, right? Now from this right angle triangle we can easily solve this problem, and this value from the example, it is 1.4 meter per second. Now this angle theta is required, so this theta and this should also be theta. Now from here we can write that sine theta is VWG over VBR. Perpendicular over hypotenuse, perpendicular we have 1.4 and hypotenuse we have 7.0. We can solve it for theta, and theta comes out to be as 12 degree, and this is 12 degree upstream because it's above the x-axis, so it is 12 degree upstream. So this is the answer for the A part. Now next it says, if the speed of the boat relative to water, if this speed is increased, then what would be the change in angle theta so that this angle remains perpendicular? Now here we observe that if the speed of the boat is increased, then we can say that if this is increased, this overall value will decrease, and if this decreases, sine theta will also decrease, so theta should decrease. Now this we have proved mathematically, but if you see it conceptually, we can say that if the speed of the boat is increased, then it should make its heading more downstream in order that its y component remains 1.4 meter per second and still lands directly across the river from its starting point. Therefore the theta should decrease. So this is conceptually, and I have proved mathematically also. So I hope you got this problem, and if you have any problem you can comment me in the comment box below. And with this, the third chapter is over, and in the next video we'll start with the fourth chapter, that is two-dimensional kinematics.